Hi guys, thanks for clicking on this video. So I'm going to go through a pretty difficult 10-mark exam question on resistivity here. This is in the new specification and it is applicable to all specifications actually. So we're going to go through quite a few calculations but also a worded question here. So let's make a start. It tells you a cable is used in a high voltage power transmission. It's told you that there's 6 aluminium wires involved and a steel wire in the middle. I'm just going to increase the thickness of the pen actually. The resistance of a length of 1 kilometer of the steel wire is that. So that's the resistance of each of these steel wires. The resistance of 1 kilometer of an aluminium wire is 1.1 ohms, so let's label that as well. The steel wire has a diameter of 7.4 millimeters, so let's label that. Diameter equals 7.3. I would always recommend you label like this. It helps with ordering the information. And straight off the bat, I'm going to convert this into meters actually. So let's say 7.4 times 10 to the power of minus 3 meters. Because if we do use this in calculation, we do have to use it in meters. It tells you to calculate the resistivity of the steel. Now there is an equation for resistivity which is given in your equation sheet for all exam boards. That's resistance times cross-sectional area divided by the length of the steel wire. So the resistance of the steel wire, because it is asking for that one steel wire, we can just take that individual resistance of 3.3 ohms. We multiply onto that the cross-sectional area of the steel wire. As you can see here, it's a spherical surface, it's circular. So the cross-section would actually be the area of a circle, which is pi r squared. Since we know the diameter is 7.4 times 10 to the minus 3, if we half that, that's what will get you the radius. So let's do 7.4 times 10 to the minus 3, all divided by 2. That'll get you the radius. You then square that to get r squared, and then you multiply pi onto that. So that'll get you pi r squared, which is the cross-sectional area. You multiply that onto resistance and divide all of that by the length of the steel wire in question. In this case, it's told you the length of 1 kilometer is used in the experiment. We again have to convert that into meters, so that's 1000 meters. And putting all of that into your calculator will get you a value of 1.42 multiplied by 10 to the power of minus 7. Now, if you struggle to remember units, I'll give you a tip to help you remember. Resistance is measured in ohms. You're multiplying onto that the cross-sectional area, which is measured in meters squared, and you're dividing that all by the length, which is measured in meters. Meters squared over meters cancel out, leaving you just ohm meters. So that's the unit for resistivity. Let's now move on to part B of this question. It's asking you to explain why only a small percentage of the total current in the cable passes through the steel wire. Well, it may be hard to realize here, but all of these wires are actually in parallel to each other. So in parallel. So what we see is that there's 6 aluminium wires in parallel to each other. What do we know happens in parallel combinations in regards to resistance? We know that the more components that there are in parallel, the resistance decreases less and less and less. Sorry, it becomes less and less. So it decreases more and more. So let's put that into words. Since there are, sorry if you find the typing a little bit annoying, you can skip ahead a little bit. Since there are aluminium, or let's say 6 even, let's be more specific. 6 aluminium wires in parallel, the total resistance across them, across all of them even, is lower. That means that aluminium wires have more current flowing through them because we know current is inversely proportional to resistance. That's applicable to every scenario, including this scenario. In electric circuits, oh, that's a bit too big. Yeah, that's fine. So therefore, aluminium wires have a larger current flowing through them. That'll get you the second mark, and then the third mark is for explaining the relationship between them, which is that this is because the current is inversely proportional to resistance. You could make the opposite argument to get all 3 marks. You can say that, well, because there's a one steel wire, it will have a larger total resistance than the aluminium wires combined, which would then mean less total current flowing through the steel wire because current is inversely proportional to resistance. Moving on to part C of this question now, it's told you the potential difference across this whole sort of junction now is 75 volts. It's then asked for the total power loss in 1 kilometers. Okay, let's have a look. We've got the voltage, we need to find the power, but we need one more variable to link all of this together. Because we know the individual resistances of each of these wires, and we know that they're all in parallel, we can find or even use the equation for total resistance in parallel. 1 over the total resistance is 1 over the first resistor plus 1 over the second resistor for however many resistors there are in parallel. In this case, there's 1, 2, 3, 4, 5, 6 resistors in parallel plus this 7th one of steel. So let's try this out. We have 1 over the total resistance in this whole combination is 1 over the resistances of each of these aluminium wires, which is 1.1. So 1 over 1.1. And we do that, add that 6 times because there's 6 of those aluminium wires. So what you probably notice is that if you add this 6 times, because the denominator is the same, you can just add the numerators together. 1 adding by itself another 5 times will just get you 6 over 1.1. So let's write this as 6 over 1.1. But then you also have to take into account 1 over the resistance of the steel wire, which is 1 over 3.3. Now when you add those together, let's do it on the calculator. So 6 over 1.1 plus 1 over 3.3. That adds up to 190 over 33. I'm going to leave it in exact form for now because it'll reduce the rounding errors. In that case, the total resistance would be the reciprocal of your final answer. So that's 33 over 190. Now that you've got the resistance as well, there is an equation on your equation sheet which combines power, voltage and resistance, which is P equals V squared over R. And we can just use that. If you don't have this equation in your equation sheet, what you can do is combine power equals current times voltage with the fact that current is equal to voltage over resistance, because we want to replace current as we don't have it in our list of variables. So doing that, we have power is, instead of current, voltage over resistance multiplied by voltage. If you know how to do this, by the way, you can skip ahead. So that's V squared over R. In that case, the square of the voltage is 75 squared, all divided. Oops, running out of space. Let's move down a little bit. I'm going to squeeze it in. Power is equal to the square of the voltage, all divided by the total resistance of this whole combination that we found, which is 33 over 190. 33 over 190. You put all of that into your calculator, and that's equal to 3.2 times 10 to the power of 4. When it's a larger number, I like to write in standard form because I've seen that appear quite a lot in mark schemes. But yeah, that's everything for this question. A bit of a difficult one here, but yeah, hopefully that made sense to you guys. If you enjoyed the video, be sure to leave it a like and subscribe. I look forward to helping you out more in the future.